So before we get started, this is my third time speaking at Hack in Paris, and I just wanted to thank Hack in Paris and SysDreams for this privilege. It's a lot of fun, and I love coming here and doing this. So let's go ahead and get started. The Internet of Vulnerabilities. My name is DERAL Heiland. I work for Rapid7. I'm the research lead for IoT. I've been doing that for about a year and a half, working on various research projects, helping with assessments around IoT, and that's just a general history of where I'm at and what I do. So let's go ahead and get started. Right there? Okay. Okay, so let's go ahead and get started. So when we get into IoT research and start looking at IoT, almost always there's this heavy focus on the hardware side of it. But when we want to look at the overall security of all of IoT or a particular product's IoT ecosystem, we need to focus on more than just the hardware for it to be effective. And the reason is so many of these components are interactive. If one fails outside of the hardware, it could lead to compromise or control of the system. It can also lead to compromise of various PII data, control data over the internet, mobile applications. And that's kind of what makes up this ecosystem. This is a model that I try to focus on anytime we're doing research or assessing IoT. And the fact that we have three pieces, specifically when you're talking about consumer-based IoT. We have the mobile, the cloud, the hardware, and of course the network communication, which is used to move commands and data back and forth. And it's important to focus on all of these, because each one of them affects the overall security model of that particular product. When we get into things other than consumer-based, there may not be a mobile application aspect to it, but often there's some kind of command and control structure, which could exist on a server, could exist on some other kind of a control system, a SCADA system, as an example, human interface device, and that also works within this whole ecosystem. So coming out of there, over the last year, we've kind of developed, kind of an 8-step approach when we're looking at IoT technology. We get into like the functional evaluation, and that literally means I set up the equipment and I use it, figure out how it works, why it works. If it's something I carry on me, I carry it on me for days or weeks, just to get used to how that technology works. If it happens to be some kind of home automation solution, I turn my house into the lab. And this is how I approach looking at IoT. From there, we get into device recon. We literally do historical research on the technology or the subcomponents or products. Are there open source pieces within this? Are there products white labeled as part of this? It's not necessarily their product. It's something came out of China. They put their signature on it. Now it's part of their IoT ecosystem. So we do that recon. That recon would also looking at FCC information. So you can pull the FCC ID off, specifically on stuff in the US and manufactured for the US. And with that information, you can go to the FCC side and you can get interesting information. You can get a complete breakdown images of the internal of these devices. You can get RF testing results. So you get a lot of information about the RF. On a few rare occasions, you can often come across some schematics. But generally, that's what we do. We look at all the device, all the information that we can farm on that device. And then we go off and we focus on all the subcomponents that I mentioned of that ecosystem. We look at the cloud and web APIs. We look at the mobile applications, the control applications. We look at the network. We look at the physical embedded hardware. We break it down, look at it. What is it made up of? What are all the pieces? Does it have USBs? If I open it up, can I find landing points where I can hook up JTAGs, UARTs? So we map out the entire piece of the hardware, and then we do physical attacks on the device. What level of access can we get to the device? Can we get through it through the Ethernet? Can we get to it through the USB? Can we attack it by tapping actually into the device itself? And of course, then we also do analysis of any RF communication that comes out of the device. Often, most IoT technologies have various subcomponents as part of that ecosystem that are communicated with various protocols, Zigbee, Z-Wave, Bluetooth, Bluetooth Low Energy. And the list kind of goes on and on and on of all the different protocols you can actually encounter, even some proprietary protocols. So in this case here, we try to analyze those. We set up like a hacker RF. We capture the data. We try to decode it. We try to figure out what makes up the pieces and parts of this. We try to use replay attacks. If we can actually decode it, can we write programs to mimic it and actually inject various attacks into the device? So these are kind of the 8 steps considered an effective methodology for examining IoT. And the big thing is during this whole process, we look at the interaction between the components. An example, if I enter a command on the mobile application, I want to look at the effects into the cloud. I want to look at the effects from the cloud to the device. I want to look at the effects from there to the subcomponents that may be communicated via RF. And I want to do this generally all at the same time. So we analyze the system and the results as we go through each one of these pieces. And it helps us get in a very effective view of the overall security of a device. Besides vulnerabilities, it also helps us to make recommendations on various improvements for security or implementation methods around security to make the product more secure. So now I want to get into IoT hacking, because that's what's fun. So over the last year, I've worked on 4 general products. Now, as a research lead, this is not the only thing I do all day long. Everyone thinks that DERAL sits at his home and plays all day long with IoT. That is what I want to do. But in the real world, this is a part of what I do. The other part's obviously working with customers and manufacturers and various government entities that may be involved in IoT and being that voice within Rapid7 for IoT. But moving into this, these are the 4 projects that I worked on. Automated lighting solution, which we'll talk about. BLE tracking, Bluetooth low energy tracking devices, those little devices that you like hang on your keychains. So you lose your keys, you can actually find your keys. I actually got 4 of them, 4 different products that were on the market at that time, and started playing with those to see, well, what's the implication? Because I saw people wearing these things all the time, and I was wondering, you know, is there any security impact? What would the risk potentially be? Do these things leak information? Could I abuse them? So we kind of looked at it that way. And then the telepresence robot, which is really cool. I don't know if you've ever seen these. It's like an iPad on a Segway. They're kind of freaky looking. You know, you can drive them around the office and you can meet various people and have these face-to-face conversations. Well, it turned out Rapid7 actually had one of these, because I started talking about them with my boss. He goes, you know, I've seen those wandering around the office. So it took me about 3 or 4 months, but I managed to get my hands on one. I haven't given it back yet. I've had it for like 6 months and no one's asked for it. So I'll probably keep it and use it to do something else evil. I don't know. We'll see. And then I looked at a GPS panic button. Now, this was kind of interesting. And the sad thing about this, none of these vulnerabilities have been fixed on the GPS tracking device or BS panic button. We'll get into the story deeper, but basically these devices were being recommended or issued by the Colombian government to protect people from potentially, high-risk people from potentially being compromised by kidnapping. And certain entities came to us and asked us, could we look at this just as a research product and let them know what kind of issues there were. So we'll talk about that in a little bit too. So let's kind of dig into this. Also, I came into Paris on Monday. I still haven't seen hide or hair in my luggage, which is really bad. Unfortunately, if people know me and see me present before, I love live demos. Unfortunately, about $1,000 worth of equipment used in the live demos is still in that luggage somewhere in Paris. So we had to compensate, but it still should be good material. So some of the issues we see with automated lightings that I looked at, and these are common, some of these are very common issues that we see on IoT technology. Unencrypted storage of data, and that's a big one. Poor encryption, you know, they're not doing, you know, we know SSL is not the end-all be-all, but, you know, it's a simple baseline that most products should communicate in, and finding in cases where that's not happening. Unauthenticated control, the ability to inject commands into the IoT technology and affect it without using the primary control systems or having any kind of security. And of course, we actually found some embedded web vulnerabilities actually on the devices, the embedded devices. that have web servers. They have the same problems that every other web server on the face of the earth potentially has. So we looked at a couple of those. So let's go ahead and dig into that. So the first one, I was looking at this device up here, the back side of this, is a Osram Lightify, Sylvania Lightify system used for lighting automation in your home. This one here happens to be the home version. I also looked at the enterprise version, which we'll talk about also, some of the issues. So looking at the mobile applications, I found out once you authenticate this device and configure it, what it does is it's set up to connect to your home Wi-Fi. But on the mobile application, we found out afterwards it was storing the pre-shared key in the SSID. And yeah, that's not mine at home. I used a test unit just in case you're like taking pictures and thinking you're going to get in Dayton High and get free internet. But as you can see, it actually was storing this data. It was actually stored on a P list. This happened to be an iOS device. The problem also exists. It also on the Android device. The thing to think about this is only used when this device is initially set up. Once it's set up, there's absolutely no reason for this data to be stored, but yet it was still being stored. And I see this over and over and over. And now if it's going to be stored, it needs to be stored encrypted if it's needed for future use. In this case, it was not. And like I said, this is a very common issue that I find on probably more than 50% of the technology IoT research that I do. The mobile applications aren't properly securing data that needs to be secured. So what's that mean? Well, if you lose this device and someone gets it, and phones and iPhones and tablets are lost all the time. It's common to lose those. So if you lose a device, think about all the IoT or integration you have on that device. And if you're not sure, I would recommend changing all your passwords. It doesn't mean the person getting it is going to do this, but the potential is there, so there's no sense in taking unnecessary risk. Now that all of my luggage is missing, one of those devices in there happened to be an Android tablet containing a lot of stuff like this. So I know what I'll be doing when I get home if I don't get it back. I have to recorrect all my lab stuff. So moving from there, we also looked at these devices had Wi-Fi capability. Like I said, when you set the devices up, they fire up a Wi-Fi access point. You connect to that Wi-Fi connection. You configure it to make it connect to your home Wi-Fi. It's generally how it works. And it turns out I was interested in the keys, the passwords that are hard-coded, which is common on the Wi-Fi aspect of these devices. And this is the home one. As you see, it's 10 characters, uppercase, lowercase, and numbers. Not the most greatest address space, but not horrible, it's not absolutely horrible. And then I start looking at the enterprise, the pro version. This is a unit that's not used in homes. This is used in places like this or office buildings. This product is actually for sale in Germany, is where it came out of. They actually had it shipped to me from Germany for testing. So when I first looked at this, I'm like, it's 8 characters. That in itself kind of caught my attention. And then I noticed it wasn't very verbose. I didn't have uppercase, lowercase, and numbers showing up. I ended up having the manufacturer send me another one, and I looked at the password on it, and it finally dawned on me they were only using hex characters, 0 through 9, A through F. That was it. We were able to fire up this device, if anyone was connected to it, throw them off, capture the reconnection, and crack it in about 2 hours. And that was using a crappy GPU, not even a good one. It took only 2 hours. The interesting thing on these devices from an attack perspective, typically these devices, when you're actually connected to your home Wi-Fi, these access points go away. In this case, it does not. You have to configure it. And this also has Ethernet, so this can easily be turned into an access point. So now you have a device potentially in a business or organization that if it isn't completely configured right and these services are not shut off, it could easily be attacked and gain access and turn, game over. The other interesting thing that I see on a number of devices, when you configure them up and they attach to your home Wi-Fi, the access point on it goes away. But if you send 1 million disconnects to the actual home Wi-Fi connection for this particular device, when it disconnects and can't phone home, it instantly goes into configuration mode, bringing up that access point, giving you the ability to literally connect into it and modify it or do other attacks, if you know the password. 10 characters, a little more complex. 8-character hex, not so. So we were looking at the home, or the pro version. This is the enterprise version. And like I said, when we go through this, we run it through all of its tests. We use it like it should be used. So I go on there, and you can log on to this device via the web interface, and it has a username and password, which you can change. So it's not the default one, so that's probably a good thing. But after going onto the system, I went into the security logs. And in the security logs, I noticed my logon name was there. And of course, what's the first thing I think is, what can I inject into this? And yes, it was vulnerable to a persistent cross-site scripting in the security logs. In this case, this was actually a laughing skull. If anyone's seen some of the stuff I do, I like to inject the laughing skull from the movie Independence Day into systems when I find this. So the actual security logs were vulnerable to a persistent cross-site scripting, making it possible to carry out any number of attacks via this method. Going on to that same premise, when we look at the actual Wi-Fi configuration of the device, it shows near-field or near-presence Wi-Fi devices, other SSIDs in the general area. And of course, if anyone's seen the research paper I wrote on SSID and injection attacks, this is another thing I quickly check out. We actually have a video on that, so I like videos. So this is logged on to the Pro version. And if we come over to the Wi-Fi configuration page, we can see Wi-Fi access points, regional ones actually showing up. So we fire up our own access point and give it its own little special SSID. Not realizing this is an excellent out-of-band injection into devices that's often never tested by security testers. They see this stuff and go on because they think it's not part of the system I'm testing, but it's an outside, out-of-band injection. So a little bit of humor. We were able to inject a flash into it, but we got to think about it from a further security standpoint. We don't need to just quickly get hung up on the fact that, oh, he just rickrolled him, that's all it was. This is another persistent attack. The people logged onto this system would be management administrator on the device. They would often have administrative rights on their network also. This is something to critically think about. And then the fact that I can execute code on your device makes it possible to carry out a number of attacks. In my research paper, it's probably the research I did a while back was probably one of the best examples that I put out there. It was in an Aruba wireless access point. In the Aruba, it actually had rogue access point detection, and it was vulnerable to this. So I could literally set up a rogue access point against an Aruba wireless LAN controller, and when they looked at the screen, it would actually inject code. It actually created a root level ID password on the device, and then it would offload the running config to a third-party web server or third-party FTP server. So this attack is really critical. Someone bring me water from over there. Starting to lose my voice. Thank you. Do that in a second. So moving from there, on the home system, as I mentioned, I don't know if I mentioned it, but there is a local functionality. So anytime we're testing a device, we're testing the entire ecosystem, not just the hardware. what happens when the cloud goes away on a device? So you have home automation. If the internet goes down, can you no longer control the heating, air conditioning, ventilation, and lightings in your house? In most cases, the answer is no, you still can. The devices, if you have your mobile app attached to your local network, it's going to go into local mode. The question is when it drops into local mode, is there any security? So in this case, it was not. There was no security, and at 4,000, we actually mapped out the actual command structure. And in this case here, if this device was on a network that you were on, this port was open, you could actually inject commands in it to reconfigure it. The demo that I was going to do that I don't have the hardware, we were actually going to make this device jump from one Wi-Fi access system to another Wi-Fi access system. And it's easily done by, it was a simple Perl script. You just send a single command to it, instantly it changes. So, got to get into a little hardware. Not too much, but we got a little bit here. So on the home device, pop it open. The first thing I see in here is a couple landing pads. So it's like, what do we think these are? And I'm hoping they're like a simple UART connection, and they turned out to be. So the next thing we want to do is let's go ahead and find some connectors. These were gull-wing connectors for connecting to it. That's just to give you an idea of the size. It's really small. It's like 1 millimeter pitch on these. So then we go ahead and solder them in place, and it turns out this side over here actually had a UART to the main processor. This one had a UART to the Zigbee Z100 processor that was on there. So it was kind of funny. I showed this to a friend of mine. He's like about my age. I showed him the device. He's looking at it, and he's like, how in the world did you solder that on there? He says, I can't even see it. I cheat. I got a microscope. And I do quite a bit under a microscope, surface mount devices and all that stuff. There's a lot of things I like to do to devices when I'm tearing them down. So having that ability to solder at that level, I think, is critical to being able to do some interesting work. So at that point, we can plug into it, and this is a standard SHICRA that does JTAG, SPI, and UART. And I just wanted to show real quick the actual data. So watch this, see if you see anything interesting. There is some interesting stuff that flows by. We connect off to the SHICRA. We run screen, and then we power up the device. When the device powers up, I hope this is the right video. There it goes. This device didn't have an operating system on it. It just had the code, and this gave you some level of control over it. One of the controls, there was some, let's keep watching. We see anything good there yet? Don't tell me it's not going to show. It may have already flowed by. Did anyone see anything good go past there? Well, there was actually a track ID and an actual password it went by if you didn't catch it. And that was used to authenticate this device to the actual manufacturers for confirming firmware. There we go. So the device, the product key, and the actual password. It had several command structures. They're fairly simple. Maybe 5 or 6 commands you can actually do on the device. This was all you could do. We pulled the firmware off the device. The firmware came down encrypted, but once it landed on the device, we tried reading it straight off the device, failed on that, so we desoldered the chip, standard SOC 8 chip, and was able to actually pull the firmware off of it and look through the firmware. Again, we didn't find anything great other than kind of what you already seen flow by. And that's the great thing about these logs, these debug logs. These are great if you can get access to them, because now I can monitor the device no matter what I'm doing to it. So I can send attacks to it. I can watch how commands go through the whole system hitting this device. And that way you can evaluate the overall security of the device. Okay, so now we move on to the telepresence robot. 15 minutes left. Gosh, I've been talking that long. So it's time for me to talk a little quicker. So real quick, on the telepresence robot, this is what the device looks like. I had it ship it to my house. Now, I would love to have done some serious hardware hacking on this, but taking a hacksaw to a $3,500 device was kind of like probably not good. You know, they were nice to send it to me. The last thing I want to do is send it back to them in a paper bag. So what we did here, we found some interesting things. Insecure cloud APIs, part of that ecosystem, information leakage, and Bluetooth pairing. It turned out, you think this iPad, that's exactly what it is. It is nothing but an iPad. You buy this unit, and then you go buy the iPad. Put the iPad on it, install their software, it's how it works. It has a cable running up here, plugging into it. The cable's only used for power, no communication goes through it. The head actually pairs with Bluetooth low energy. There is no, in the pairing here, there is no validation of the pairing process. It can only take one pairing, but if somebody in the office decides to shut the iPad off, it becomes an instant target for anyone nearby. You can download the software, throw it up on your machine, connect to the Bluetooth, and take over the device. Of course, you can't see where you're going, but you can still make a hell of a mess. It doesn't go super fast, which is probably a good thing, or I would have destroyed it by now. When I first got it, I ran it straight into a wall in the house when I powered it up. So, moving from there, we start looking at the cloud APIs. So it turned out there was no authentication, and we had this offset. What I did was you put a high number in there for an offset, and it'll tell you what the max offset is. What this is used is tracking all of the session data for every robot that is ever connected to the system ever. So you basically take the limit right here and set it to a high number with the upper level offset and dump all the data out of the system. And this is all the session communication data. I blocked this stuff out because this is potentially data that could be used to take over a robot. And I don't want you taking over my robot. It needs to be left alone. Sitting in the corner being nice in my house. I don't need it waking up some night driving around. So we found another one here, and this is with the installation key. When you set up a device, it registers an installation key. You can re-register a device multiple times and get different users. It's based on how the robot's logged in. So in this case here, we can do the same thing with offsets, but in this case here, we can actually pull latitude and longitude. So we can pull all the offsets, and then we can use that to pull all the latitude, longitude for every robot on the face of the earth. Probably not a good thing. This has been patched also. This one here, way worse, but somewhat mitigated. Turns out, and this has been fixed also, turns out the robot, if you can man in the middle of the robot to the cloud, or you can actually get physical access to the robot, you can get this thing that's called a robot key. With the robot key, no authentication, which everything I've showed you is no authentication, and you send the robot key to the cloud, it dumps a list of every users that can remote control that robot and a session driver token that always stays valid. That driver token is nothing but the web management session token for every connection to the robot, giving you the ability to completely take over the robot over the internet. So disgruntled employee, you know, he walks over the robot, you can basically pull his data off of it. Now he can control that robot no matter where he goes, until they deregister the robot. So some interesting findings there. So moving on to the Bluetooth low energy dongles. This was kind of interesting. We found some interesting vulnerabilities. The demo I was going to do was with a live device. So, but I don't have a live device, but I did film some of it. I'm hoping everyone can see this okay. Yeah, it's not too bad. This happens to be my Android tablet. And what we're going to do is, as this is running, we kind of think about it. If I'm a bad person and I come in here, I can detect using, information on local devices. This is NR Connect, showing me all the devices that are in that location. And I can find one of these tokens. In this case here, we got several different brands, but the one I'm talking about is the TKR, which is the Tracker Bravo. We can get information down here like these IDs. These IDs is the actual tracker ID in reverse. It's also, that's the tracker ID, it's the MAC address in reverse. This is used to track the device or identify the device via GPS. So from here, we're able to actually connect to it. So if someone's in a room, you can fire that up, you can identify the device in the room, you can connect to it with your device because there's no pairing. And at that point, it's connecting. We can get a certain amount of information, GAT information. In this case here, we're looking at, where is it, the one I want to look at? Immediate alert. So now I can identify who's actually holding that tracker by looking for the person who's trying not to look like an idiot because the alarm went off on the tracker. Should be easy to spot and hear. So I can set the alarms off on these devices remotely. So no alert, high alert, or you can drain the battery on them. So it's pretty impactful. So, okay, now I can identify a device in a crowd. I can set off the alarm and identify the person that has it. I can identify the tracker ID. Where it all kind of comes to a head is when we get to the cloud APIs. We take that tracker ID we pulled, and now I can get your latitude and longitude. So this ability to figure out who you are, figure out the device you have, gather your GPS coordinates no matter where you're at, as long as it's in close proximity to your phone, because your phone's what's being used as that ecosystem to send up the GPS coordinates. Now, if you lose the device, anyone else walking by with that same application will detect that device and send up the GPS coordinates, and that's how you use known as cloud or crowd GPSing. And it's a common thing for these tokens. Okay, so now we get into the panic button. And it turns out that, like I said, the Colombian government was actually issuing these devices. So the AP, Associated Press, who had people using these devices, came in and asked me if we would take a look at it. And it's like, cool, this ought to be fairly interesting. So we found poor design, like horrible, horrible design, okay? Non-SSL communication, GPS data being sent up to the cloud without any authentication. The application running inside had some bounce check issues. It wasn't exploitable, but we did identify it and we pointed it out. And then, of course, their real-time web interface, total fail. So the first one to look at here is, like I said, that whole recon part and using the device. The device uses SMS messaging for configuration. Okay, so you can use SMS messages to configure it to call any number, to do all these different features. But what happens is you can also set a password. So you set a password to protect it. It's a PIN number, okay? So now people can pull information or configure it with SMS messages. But they actually built into the product that you can use reset, which will set it back to the factory without a password. So if this device is being used by somebody trying to be protective of being kidnapped by Colombian drug lords, and you have their phone number, you just send them an SMS message and the device is rendered useless. So pretty bad, but it shows that whole recon and testing the device from all those 8 pieces I was talking about. We found a vulnerability or a design error just by reading the manual. The next one was, if there's a password on one of these devices, could I identify this device setting at the end of the phone number? So if I had a phone number and I wanted to know if one of these devices were there, could I identify it? Well, the reboot command, like they mentioned before, could be done remotely without a password. It's not true. You actually had to have a password to set a reboot. So what I did was we pulled the firmware, and I went through the firmware, and we found a unimplemented command that was a reboot exclamation point. All it did was return a format error. In that case there, you did not have to have a password. So you could basically do like SMS war dialing. So if you know there's a range of these devices by people in a certain country, in a certain city, you could easily do war dialing or SMS dialing and wait for responses back and identify whether that device is potentially one of these devices. And then the bounds check, this was based on looking at information. We dumped the firmware, or we dumped the flash. On the flash, we've seen all the configuration settings. But I noticed the spacing between all the configuration commands seemed to be fairly narrow, and I wasn't sure where there's bound checks. So what we did here is, this is the command A1 is used to set the phone number for the first phone number it dials. So in this case here, we just made it longer, and when we run it, it runs through okay, but as you see, we ended up overwriting the second phone number that needs to be written. Now, initially when I started testing for this, I was just like shooting from the hip and freaking bricked one of the devices. So it overwrote something, but I didn't think it was close enough to the code, so I'm not sure what got corrupted in there. Didn't really get a chance to follow up or see if it could be leveraged in any way. I don't think it was. I just think I just screwed up the whole structure associated where it was reading to identify how to proceed in the application. Okay, and when we get into the cloud part of this, the web service, the real-time web server is part of this. This is sending data up from this device to the cloud. We turned out that you see they have a user ID. That's basically every device that's been issued, everyone that says an account. There's no authentication to this. So if I post this all tracker data, I get the EMEI number for the cell device, and I also get it's just the EMEI number. Well, with that data, you could do a lot more. So with the, IMEI, I always get that ass backwards. But with that there, you could actually poison. It turns out that the real-time tracking system goes over port 5050, and yet it's not encrypted. So I constructed a program to actually be able to inject this data up there and alter the GPS coordinates of the device, so making it possible to move it somewhere. So my test device, which was Dayton, Ohio, instantly jumped to Moscow by being able to poison this data to affect the actual data here. So I'm not sure if I have any more time left. We have time for questions. So I hope you guys liked that or found that interesting. Any questions?
We have time for a question. Anybody have a good one?
Yes, yes sir.
In case of VGA system on chip, how do you route them to the header file?
BGA chips, I have to admit, I find to be. Oh, okay. So how do you effectively root a device with BGA processors on board? It really comes down to tracking out all the connectors on there. Are there any connectors? All the wires coming off the BGA, obviously I can't hook into it. It's a BGA. And if I desolder it, it's impossible to do the ball grid arrays back on unless you're like really good and have the equipment, and I don't. So often in that case is I'll flip the device over, and I have one at home right now I'm actually working on. It turns out it looks like everything's passed clear through the board. So then I scrape off all the finish and I tap in freaking 50 million wires on the device, and then I pull down the data sheets. Now, data sheets may give me a general idea of layout, so there's certain things I can test on there to maybe get orientation properly, how it came through the board. And I literally try to map out the structure of the BGA on the back side. And at that point, I will attempt to test into it. Is there any exposed J tags, serial wire debug? Does it have any SPIs? Is there a UART in there? And then we'll go through that process and try to test for all those. Am I successful? A number of times in the cases with those, it gets real frustrating, real time consuming. But that's the typical approach that I take. And like I said, I got one at home I'm doing that with right now. So thank you very much. I appreciate you coming.